The space agency, known for exploring the cosmos, also operates a permanent research laboratory 19 meters below the surface of the Atlantic. Since 2001, NASA has used the Aquarius Reef Base for its NEMO project. Here, teams of aquanauts live in isolation to simulate the cramped, unpredictable conditions found on the International Space Station. This model shows how much we know about our planetary neighbors. We have high-resolution data for 99% of the Martian surface. That zooming back to Earth, our knowledge is surprisingly limited. We have mapped less than a quarter of our own ocean floor. The deep sea is a realm of absolute darkness and staggering physical stress. At extreme depths, the pressure becomes thousands of times greater than at the surface, creating an environment as hostile as the vacuum of space. This underwater training serves as a testing ground for a much larger mission, applying everything we learn about Earth's oceans to find life in the vast hidden seas of the outer solar system. For decades, scientists believed the deepest parts of the ocean, like the Mariana Trench, were barren. Without sunlight to drive photosynthesis, the environment seemed too extreme to support a complex ecosystem. But the discovery of life in these trenches proved that biology does not require the sun. Deep in the darkness, researchers found entire worlds thriving in total isolation. These organisms are surprisingly resilient. Researchers found clusters of 3-meter-long giant tube worms and alien-looking big fin squid that have adapted to endure the crushing weight of the deep ocean. They survive through chemosynthesis, clustering around hydrothermal vents to draw energy from the heat and minerals released by the Earth's crust. This biological discovery has changed our criteria for where life can exist. If organisms only require water, heat, and minerals to thrive, then the dark, high-pressure oceans throughout our solar system are no longer barren zones. They are viable targets for discovery. Jupiter's moon Europa is the primary candidate for this search. Beneath its icy, fractured shell, it holds a saltwater ocean containing twice as much liquid as all of Earth's oceans combined. To study this moon, NASA developed the Europa Clipper. Its mission is to map the icy crust and determine if the hidden ocean below has the chemical composition necessary to support life. Future exploration will require cryobots, nuclear-powered probes designed to melt through 15 kilometers of ice to deploy autonomous submarines into the dark, high-pressure sea below. Further out at Saturn, the moon Enceladus is actively venting its interior into space. When spacecraft analyzed these plumes, they detected hydrogen and complex organic molecules, the same chemical foundations found in Earth's deep sea vents. NASA is also preparing the Dragonfly mission for Titan, Saturn's largest moon. It will land a rotorcraft on the surface to investigate how life might evolve in alternative environments of liquid methane and ethane. These missions are exceptionally difficult. We know that the pressure in our own ocean trenches can implode an underwater drone. Surviving the seas of an alien moon means we must first master the depths of our own. The global effort to map Earth's ocean floor is accelerating. Through the Seabed 2030 project, high-resolution coverage has increased from just 6% to over 23% in recent years, utilizing the same sonar technology we use for planetary exploration. This mapping project is vital for understanding the ocean twilight zone. This deep layer of water is home to a vast ecosystem that regulates our atmosphere by filtering and storing massive amounts of carbon dioxide. NASA tracks this process from orbit using the PACE satellite. It monitors the health of ocean ecosystems and provides data on how marine life influences global climate cycles. The high-resolution sensors and autonomous vehicles designed to search for alien biology are now being adapted to monitor Earth's own health. These tools allow us to track how the ocean regulates atmospheric carbon, providing the precision data required to understand and manage our own climate. The massive multi-billion-dollar investments into deep space probes and underwater laboratories aren't just for gathering data. The discovery of even a single microscopic organism in an alien ocean would shift our understanding of human history. Finding biology elsewhere would prove that our existence is not a local anomaly. It would demonstrate that life is a cosmic rule, a standard process that occurs wherever the right conditions align. By looking into the most hostile, unmapped depths of our own world, we are building the path to prove that we are not alone in the universe.